Good morning. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 38, on the atom and the quantum. You have probably already seen in pictures and representations the Bohr model. It usually looks something like this, and they like to draw the atom with various electrons spinning and various orbits, and then you see a bunch of protons and neutrons, usually the colors of different colors, making up the nucleus in the middle here. And we like to draw the connection that we have between that, and when you see those pictures of the solar system, you have various planets. You have Venus and Mercury, and here's the Mercury. We got Mercury and Venus and Earth, etc., etc. So people, we love it because we just love, when something looks like another thing, and it's just really cool. And it's very intuitive. But the Bohr model has limitations in the same way that the solar system model has limitations. If you actually zoomed way out into space and turned around and looked at our solar system, it would look a lot more like this. Tiny little dot. I mean, this would still be bright, but these would be so tiny. So to give an idea of how much empty space there is if you shrunk the Earth down to the size of a pea, shrunk all of the solar system down until the Earth was the size of the pea, the sun would be the size of a basketball 40 miles away. That's how far away we are.
A million peas can fit into a basketball?
Look, maybe the basketball pea thing isn't exactly right, but the 40 miles away is the part I'm trying to get across to you. It's very far away.
Jupiter was a basketball.
Okay, maybe it was way smaller than a pea. Maybe it's just a really small pea. I don't know. Well, anyways, basically, the Earth, the sun, when we draw our solar systems, it's no fun to draw a solar system where you just see specks and most of the page is empty. And so that's why we draw it, with our sun looking beautiful and big. In the same way, if I was going to draw this model of the atom more closer to what it actually is, the proportions, the nucleus would look so small because you could fit 3,000 nucleuses edge to edge inside this inner ring of this atom here. And so it's mostly empty space. And then these electrons are 2,000 times smaller than a single proton in there. So they would look very tiny. Remember, it's mostly empty space. Remember, if you actually crushed everything down where the masses were touching each other, the entire Earth and everything on it and everything in it would be about the volume of 2 tablespoons. That's what neutron stars are, that dense. 2 tablespoons of a neutron star would weigh as much, or would have as much matter as the entire Earth. Because remember, most of matter is actually empty space, and the electrostatic repulsion, or the repulsion of the electrons, the repulsion of the electrons is what's holding things away.
Of that in my cup with my cup, right?
I mean, yes. Okay, so I'm just imagining all the effects of that. Someone's probably made a cool YouTube video simulation of that. Okay, so.
Would it make a little deep?
Whoa. Wait, we gotta keep going, Okay, so another way, one way that remember that the Bohr model isn't accurate is not only is it the scaling issue, but another way to remember the Bohr model isn't quite accurate is that we like to draw these beautiful orbits, but an electron is not following a beautiful orbit. An electron is following, so it's more like a fuzzy cloud, that the electron at any moment is kapwinging around at that general radius. So for this guy in the middle here, he's kapwinging around, you can imagine, 3 dimensions in that general radius. So he could be doing ding, 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 ding. He's staying in that general radius. That's sort of like a fuzzy cloud that approximates, he's somewhere in here, guys. And then this shell here is somewhere in this general radius. So if we actually drew the atom model trying to look more the way it really is, it would look more like fuzzy cloud shells. But even that isn't perfect because we're dealing with things so tiny that we don't actually completely understand. So all of our models can be useful, but if you actually shrunk down and if you somehow, actually shrink down and seeing it, and then there comes the whole problem with the wavelength of light, what it means to see and all that. So these are we call them models, to try to sort of approximate something deeper than we can explain. Well, anyways, now let's talk about light. So light, there's this debate going on about what is light. There were even people that thought there were particles that streamed out of your eyeballs. There's all sorts of very interesting theories people had about light. So light, is it a particle or is it a wave? So is it more like an atom, or is it more like sound? But wave requires a medium, right? A wave requires something that's actually moving. Like sound requires all those, air molecules moving. So there was this huge debate, and Pythagoras, the guy that we get the Pythagorean theorem from, ancient Greek guy. Well, anyway, I don't have to write all their names down, but Pythagoras thought it was a particle. Aristotle, another Greek guy, thought it was a wave. And people had their different debate about is light really is it like a thing, like a particle, or is it more like like the energy moving across the medium? And so there was this whole thing of, is light traveling through the medium, is the ether, and is it really traveling through the ether? So there was all this debate raging back and forth. And Newton actually thought it was a particle. But in 1801, there was a man named Young in 1801 who did an experiment, the famous double slit experiment. Guys, I sent out a YouTube video simulation of this. Go watch it. The double slit experiment is one of the most important experiments in physics. And it's literally just made by a guy had a piece of metal, put 2 little slits in it, and you put a light bulb on the other side. And watch what happens. It has huge, huge repercussions. So you got the screen here with 2 little slits, and you got a light source on the other side, okay? So as you can imagine, you got this little pinprick of light coming out. And then he had like a projector screen here to see what happened on the other side. So what would you predict would happen? Well, you might think, well, there would be a bright spot here and a bright spot here, like where the light streams out, like a flashlight, like a laser or something. That's not what happened. Instead, he got a pattern of light and dark and little, what we call it, interference pattern. You say, well, how in the world are all those little spots of light when there's only 2 points? Waves. You see, as the light comes through this and it makes a wave, like it's like dropping, if you've ever dropped a rock in a pond, a still pond, and you see the waves propagate out. Okay? You say, well, how do you get the stripes of light and dark? Well, this guy, remember? This guy's also. Now, if you ever go to a pond and throw a rock in and throw in another rock next to it, and you will see this pattern. And it's a pattern we like to call wave interference pattern. And what happens is where both waves are going up, like right here, you're going to get a peak. And where one wave is going up and the other wave is going down, it cancels out. Remember, you've got when you have one wave doing this, and then you have another wave doing the same thing. If it's doing the same thing, then they add, and it looks like that. But if you have one wave doing this, and then you have another wave where its trough is crossing here, then they cancel out. And you can see this. Go to a still pool or still water and throw 2 rocks in, and you will see their little ripples go, and you'll see parts where the ripples cancel each other out, and the parts where the ripples reinforce each other. 2 troughs will make a deeper trough. A crest and a trough will cancel out. 2 crests will make a higher crest, and you get this interference pattern rippling across. And what those little bands of dark and light here are actually just the interference pattern of where the waves cancel each other, where the light cancel each other out, and where it got brighter. So brighter, darker, brighter, darker, brighter, darker. So what you're seeing is proof that light is a wave. So people are like, case closed, light's a wave. There we go. But there's more. Then there was the photoelectric experiment. The photoelectric experiment is they had a metal, and they would shine that would release, if it got enough energy on it or enough light on it, it could release an electron. So it's cool. You shine a flashlight on it, light hits it, and the kapwing little electrons go off, flying off. Okay. Then they said, yeah. Oh, well, you can measure them. Well, anyway, so then they said, okay, now let's try that again, and we're going to do it with a red flashlight. So they put a red flashlight on, red light. Does this red show up on the camera? Can you see? Yes. I'll leave my skinny Sharpie. So they did it with red light, and I apologize. This Sharpie
Sort of. It looks pink.
Yeah, it's supposed to be red. I wish I could find my red.
It looks
Sharpie.
pale
Red.
pink.
Anyway, so they did it with a red light. No electrons came off. So they said, okay, we'll get a brighter light. The white flashlight worked. So they got a bigger flashlight, massive flashlight, and they just poured that red light on. That's supposed to look really nice and dark and red, but it's not. But imagine it's very nice and dark and red. No electrons came off. So then they went and they got a little blue flashlight. Pathetic, tiny, very, very dim, almost nothing. And they said, what is going on? We know that the energy of that red flashlight was much, much greater than the energy of that blue flashlight. So why is it that a pathetic, very dim blue light can release electrons, but the big powered red flashlight can't? Why? And Einstein says it's because light is a particle. So remember this model we have here? Do you remember we talked a little about like how the neon light tubes work? I think it's even how the old fluorescent lights work. It's how your glow, if you've ever got this like little glow in the dark stars, it's also how they work. Remember like glow in the dark beads? You charge it up by putting it on something light, then you drop light, go into a dark room and it glows. What's happening there is you are exciting, when you are putting it on a light or whatnot, you are exciting those atoms, putting energy into it. When I put my glow in the dark beads up against the lamp, I'm pumping light into it, and what happens is that energy turns into bumping these electrons up into a higher energy state. And they're bumping them further out, and then when I go turn off the light, go into a dark room, what happens is then they're not having all that new energy input, and these guys aren't going fast enough. In the same way when you're swirling a marble around in a mixing bowl and you just stop moving it, you stop pumping energy into it, and you'll watch that little marble spiral down to the middle. What's going on here is these little guys have to get down. So then they hop down, and when they're losing energy and they hop back down, they emit a photon. And depending on what element this is and what spacing there is and how far they hopped, that photon will be different colors. And that's how they get. Whatever phosphorant stuff they use in like the little kitty beads is green, but I believe there are other kinds too. I think they're just more expensive. Like phosphorant, like some natural phosphorant rocks, it's like a blue color. I think the green is the cheapest. But anyways, but neon tubes, you will get different colors in those like neon signs. I know in this world of LED lights, you guys probably don't see those as much, but when I was growing up, neon signs are more of a thing. And you would get a different color in those neon tubes depending what gas you put in. Because the different atoms, different gases, they have different, their electron shells are in different positions.
So what exactly
different
is the neon
distance,
sign?
different. We will get to that later. I need to get on with this so we don't take too long. Okay, so neon signs. Okay, neon signs. They're tubes. They're glass tubes, and they've got a gas in it. And then when you flick the electricity on or whatever, they have a thing there that's exciting the atoms, and it's flicking it back and forth, and so then the atoms are getting excited and then de-excited, and so the electrons are jumping up and down from the energy that you're putting in. You have to turn it on, but it's actually flicking it back and forth. And so every time it flicks off, those little electrons jump down and emit that like bright purple or bright pink that you see, or bright green.
I don't think I've seen this.
And so especially huge cities used to use like neon signs like over their shops and stuff to make you notice, because it's a bright color, and their sign is usually made, like the letters were made with the glass tubes, so you would see big. I know, so it looked kind of cool. I guess all of that is like technology from an older era. Now we have LEDs, you can do so many more things, so it's not as like, whoa, they can do that. They put their name of their shop in bright pink, and now you can do all sorts of things. But it was cool. Anyway, so that was the science behind it. And I think even fluorescent light tubes, that was also the science behind it, jumping up and down. But now we're all switching over to LEDs because they work better, or they're brighter. You get more bang for your buck. Okay, so where are we?
Mommy.
Photoelectric effect. Right. So in the same we gotta finish this.
that?
In the same way that the photoelectric effect that we're seeing the photon jumping out here, what Einstein theorized is that basically all light comes in these little packets. And the electron, the atoms in here, their little electrons, can only absorb one of the light packets. And that the light packets' energy are different. Each energy of each light packet is the energy of that light packet is the frequency of that light. So remember how red light, it has like double the, I'm probably getting the numbers way off, but something like 600 nanometers. So the frequency, is the inverse of that. I mean, of and the frequency of, what did I just say? Red light has longer wavelength. Like it's about twice the wavelength, I think, than blue light. So blue light has like double the frequency of red light. And so you plug this in and you see that the more tighter your wave is, the higher your frequency is, because remember frequency is pulses per second. The higher the frequency is, this is a constant. This number is just Planck's constant, and it's a very tiny number, and I wrote it down because I did not memorize it. And it's 6.6 times 10 to the negative 34. That's if I moved this 34 times. That's how tiny this little guy is. Tiny little number. So this is Planck's constant, okay? Planck's constant times, so to find out the energy of any packet of light, you just plug the frequency in and it'll give you the energy. And so you see here, blue light has more energy in each little photon packet than the red light. Now you might say, but wasn't there even more energy in that massive red flashlight that we shined on? Because it had so many more photons. The key is that each little electron here could only absorb one photon. And the red photon just wasn't enough energy to get it escaping from the metal. But the red photons just didn't have enough. It doesn't matter if someone gives you 500 tickets to Florida, that you can only take one ticket, it's not going to take you to Hawaii. Even if those 500 tickets to Florida cost a lot more money than one ticket to Hawaii, you can only take one ticket. It didn't matter that there was that giant red flashlight just bombarding with all those red photons. Each of those electrons could only absorb one, and so they couldn't escape. But with the blue light, even if it's a dim blue light, it's like handing out those tickets to Hawaii. Maybe not a lot of electrons leave, but as many as that you're able to give blue photons, those electrons can leave. They got their ticket, they're going. So this is actually what Einstein won his Nobel Prize in Physics for. People think it was relativity. It wasn't. He actually won it for
What's
this.
relativity?
Not in this lecture. Later. We'll do relativity later. Okay, so here, what he theorized is that light comes in packets, in particles, that he called photons, or we call photons, and you can find the energy of that photon just by multiplying its frequency by Planck's constant, and that will give you the energy in it. Okay. So, the end of the day, Young's slit experiment proved that light is a wave, and the photoelectric experiment proved that light is a particle. So we call that the particle-wave duality of light, that it's both true. And it kind of makes your head hurt, and it's kind of interesting. And
Hey, light makes your head hurt?
no, just trying to understand, how is it both?
Mama, do the LEDs.
Now, one of
The
the...
LED signs make it harder.
The LEDs? Well, LEDs turn less of the energy into heat than like other things.
Like LEDs?
No, incandescence, if you touch an LED bulb, you're not going to burn yourself. If you touch an incandescent bulb, you will burn yourself. I even melted a plastic lampshade with an incandescent. And that's one of the reasons everyone's switching to LEDs, is because LEDs turn more of that energy into light and less into heat.
Making your head
Where
hurt.
incandescent light turns a lot of the energy into heat. And so usually people aren't using light bulbs to make things hot. And so they want
You were talking
LEDs is
about your
cheaper.
head hurting.
Getting there. Okay, so this is something interesting, is that light is both a particle and a wave. And this is something, a lot of times people are like, I'm not into all the crazy mystical stuff. I'm just like what I can see with my eyes, just real down to earth things. Like, this is about as simple as you can get. This is light through two little pinholes. This is flashlights shining at metal. This isn't like some great mystical strange thing, and yet it is mystical and it is strange. And you're like, how are they both true? And this shows the limits of our understanding. That even dealing with things like metal and flashlights and poking two holes in a piece of paper, or two slits, I should say, two slits in a piece of paper, the double slit experiment. Even doing this, we can meet things about reality that is hard for us to wrap our brains around. It shows the limit of our understanding and our reason. Like, it's true. The truth is bigger than like what makes sense in my head. Okay, hold on to this because it's going to get even weirder. At the end of the lecture, we are going to talk about something that makes this double slit experiment even weirder, and we're going to touch on quantum mechanics. But first, let's go back to the rest of this lecture.
Does that have to do with cats?
No, we will leave the dead cat alone.
What?
Okay, now.
Can I pause it?
Wait, no, do not pause it. Do not pause it. We gotta finish this. Okay, you can see the photon or particle nature, light. Oh, so one of the ways you can see the photon particle, the photon, that its particle nature, is these grainy, underexposed photographs that you're actually seeing like where the photons are hitting, and the more they're underexposed when they don't let enough of the light hit it. It's like you see this really, really grainy image, but as they let more and more of the light hit it, it's like it increases the resolution and it gets better and better. And you're actually seeing those little ka-pwing, ka-pwing, ka-pwing little photons hitting it. It's pretty cool. Okay. So now we can get even weirder. We're going to say, okay, so if light that we knew from the double slit experiment is a wave and how it acts in various mediums, all that, if we know that light is a wave and yet it is a particle, then are things that we think are particles really waves? Really also waves, I should say? So let's say, what about electrons? Electron's a particle, right? Is an electron also a wave? And the answer is yes.
Is mommy also a
We're
wave?
getting there. The answer is yes. They did an electron beam with a double slit experiment and they got an interference pattern. It's pretty cool. That's actually how electron microscopes work. When you're using a regular microscope, remember you're getting a light wave, and when you look at anything, you're seeing how does the light bounce and reflect off of it, okay? So let's say we get a little round thing and the light bounces in a certain way, and your eye will see that, see the bouncing pattern, the bounce back pattern, and your eyes will say, okay, that thing is round. But now what do you do if the thing you want to see is actually smaller than the wavelength of light, of visible light? Suppose the thing that you want to see, the weird little shape of, looks like this. But if you see, if it's much smaller than the way it's gonna bounce, maybe you don't even see it because it's so small. Like the light.
That.
What I'm saying is the light. If the thing you're looking at is smaller than the wavelength of light, you can't really. You might see like a blot. Or there's something there, but that's about it. You can't get any resolution. Wait. I'm getting there. When you see some of these amazing photographs people show of tiny things. Super tiny things. They also do like the heads of flies, and you can see every single hair, and it's kind of gross. Or those tiny little flies. No, but when microscopes are still using regular light, electron microscopes, they actually use a stream of electron particles because the wavelength of an electron is much smaller than the wavelength of visible light. And they found the de Broglie wavelength. So de Broglie, his theory was that every particle has a wavelength associated with it. This is Planck's constant. Remember that really tiny number? This is Planck's constant. So I'm going to just square it. So remember, this is the constant, Planck's constant, over the momentum of that particle. So we can plug in the momentum of a electron, because remember, it's got a mass, it's got a velocity. We plug it in, and we get the wavelength of electrons. And that is why electron microscopes, because if this was the wavelength of, visible light, the electron microscope is much tinier wavelength. And electrons have much tinier wavelength. And so they can see those tiny microscopic things in nanofabrication when they're testing to see, okay, we made this device, are the contacts meeting the thing? They can't look at it under a microscope with regular normal light. It's too small. They won't be able to see. So they put it into an electron microscope, bombard it with a stream of electrons, see how the electron interference patterns and whatnot bouncing off it, and then they take that and they re-image it, image it into, they image it into a big photograph. We look at it and then we can see, oh, that's what happened with that nanofabrication device. So that's something really cool. Okay, so now we say, all right, if things like electrons follow this, what about a bullet?
What about?
Does a bullet have a wavelength? And the answer is yes. But it is extremely small because you can calculate the momentum of a bullet, right? You've got your mass of your bullet, your velocity of your bullet. You just plug it in, Planck's constant, still Planck's constant. But the momentum of a bullet is so much greater because it's so much more massive than an electron. And so you end up with a wavelength of something like the wavelength of a bullet is something like, I think it's 10 to the negative, oh wait, did I write down the wrong? I think I just wrote down the wrong thing for Planck's constant. No, I lost it.
Mom, I'm gonna pause it.
I'm gonna pause it.
So bullets have a tiny little wavelength. To get a sense of this wavelength, it's a millionth of a width of a hydrogen atom. So you aren't going to get to do the double slit experiment and see those nice little, this is going to have to be the millionth width of a hydrogen atom. You aren't going to really be able to measure that. But it exists. This de Broglie wavelength for a bullet exists. It's just, the bigger the momentum in the bottom, the tinier this thing is. And so it is so tiny. So tiny that you aren't going to be able to measure it, unlike, say, an electron beam, you can measure the double slit interference. So in the same way, you can say, actually, even you driving the car, your car has momentum, right? Plug it in, find the de Broglie wavelength for it. It's not going to be something you can measure. And it has no effect on our daily life, which is why we don't normally think about it at all. By the way, de Broglie is spelled really weird, like that.
That's a
I used to call it the de Broglie wavelength, but it's not. Okay, it's de Broglie.
Mommy,
Okay, yes.
there's something about the light interacting with photons. There's something like on the window at night we can't see the dirty stuff on the place where the light is in.
Right, you see because of light. So if there's no light there, you can't see.
It looks like I can see because I can see through it to the other side.
Through the glass?
Yeah.
That's because there's light.
But it doesn't look like
There
the
is
glass
light.
dirty.
Oh, you're talking about the dirty stuff on the glass. Yeah, if the light is interacting with the stuff on the glass, then you see it. When it's dark enough, there isn't enough light to interacting with the smudges on the glass that you don't notice. I see what you're saying. Okay, so now back to spectroscopy. So remember those shells we talked about and how the atoms jumping, excited atoms jumping, from different shells, from the different levels, the different shells, release different colored photons. But you may ask, but why? Why does the thing jump down and release a photon? Why doesn't it just decide to orbit here or here? Why is it only orbiting in these distinct shells? And if it's going to drop down, it has to release that extra energy as a photon. It's not quite enough energy to cut it in here anymore. It's coming down here, but it has a little extra, and so boom, jettisons off, and you get that, neon photon or whatever. Why doesn't it ever go between the shells? Why? And this can be explained following de Broglie's wavelength theorem thing. Is that if those electrons are really like waves, you can imagine that a wave, so say this is our electron, we've got one wavelength. Suppose I'll put two wavelengths, okay? So each of these shells has to be a multiple of a wavelength. Because this first guy, imagine we took a wavelength. I'm trying to take this wavelength and stretch it around. This is like one wavelength, okay, that I wrapped around. Often in illustrations and stuff, they like to take a piece of paper and you draw one wavelength, two wavelength, three wavelengths, and then you wrap them, and then you get shells of them. If you wrap them this way and look at them, they kind of draw it like if you get a strip of paper and you get, here, one wavelength, and then you have another strip of paper where you have two wavelengths, and then you get another strip of paper with like three wavelengths. Sorry, I'm drawing very ugly waves, you get the idea. And then you tape them around, and you will see that they're quantized. Basically, they're an integer. They have to be an integer number of that original wavelength. So it's kind of like if I make a Duplo tower out of little bricks. Can you go grab me a Duplo tower? Oh, sure. Or if I make a chain from paper clips, like my chain can only be as long as some number multiplied by those paper clips. I can't build it with half a paper clip. So in the same way that we say light, light is quantized with the little photons and whatnot. Here, the electron shells are quantized because of that electron de Broglie wavelength. That it has to be a multiple. You can't just be in between. In the same way, here, this is good enough. If I've got this Duplo tower here, and I'm building the Duplo tower, it's quantized. This Duplo tower is quantized by the size of one brick. So if I want to make this taller, I can't make this half a brick taller. I'm using these bricks. They've got to be a multiple of this brick. So we'd say this building with Duplos is quantized.
There is such a thing as a half.
There it goes in lots of little pieces. Okay.
There
We're on
is
together.
such a thing as a half.
Okay, so in the same way, we've got wavelengths, sweetie. We've got wavelengths here. The electron shells are quantized by the wave has to close in on itself. It's got to be that complete, little wave. So we're making these rings. It has to be a multiple of that wavelength thing. Okay. So the electron is actually a wave. It must wrap around in waves.
Wait, I'm a wave?
Each wave is a fixed length. Shh. So each circumference has to be an integer number, a multiple of that wavelength. It's quantized. Okay, now we're going to do a slight digression and talk about the size of atoms. And why is it that helium escapes from a balloon much faster than hydrogen does? But you know that helium has 2 protons and actually 2 neutrons, and hydrogen only has 1. So you would think that hydrogen would be smaller and leak through the balloons faster. But no, helium leaks out faster. You say, why? And that's because, yes, very cool, very cool. So if you look at a picture of a helium atom, it looks something like this, okay? One little proton, one electron. But if you look at a picture of a hydrogen atom, it actually looks something like this. There's 2 protons, 2 neutrons, and 2 electrons. But it's smaller. Helium takes up less space and less volume than hydrogen, even though helium is like 4 times as dense, because we got those 2 protons and 2 neutrons, and with helium, we've only got that one little hydrogen in the middle. So we said, why does helium take up less space? Well, for the same reason that you are pulled in more to the Earth than, say, a small light planet. Wait, let me finish the thought. And so because remember electric charges, this is plus, this is minus. Now you've got 2 pluses. So even though it's balanced, from somebody outside the atom, the charges cancel, right? But when you're inside, when you're in the war, it's not, oh, well, it was just as easy as fighting 1 guy as fighting 2 guys or whatever, because you're in there, you're in it. When you're in there, that little, yes, he's got his little backup buddy over here, but he's getting pulled in by two positive charges, where here it's just 1 positive charge. And so it actually shrinks the size of these. So this is why it leaks out of balloons, rubber balloons, easier because it is smaller. It's easier to slip through those rubber molecules because the size of it is smaller than the hydrogen. So you may say, well, why don't we fill up all of our balloons with hydrogen? Well, they kind of tried that already. If you ever read the Hindenburg disaster, where they made this giant blimp, like a giant balloon, and they filled it with hydrogen because hydrogen was less leaky, and the whole thing, hydrogen is very flammable and it burned. And actually, we do fill balloons with hydrogen, weather balloons, where they're not worried about, it burning and blowing up in the faces of small children at a balloon party because it's way up in the sky. Weather balloons, they actually use hydrogen. Yes, what's your question?
Wait, but helium is less dense than regular air, right?
Yes, that's why it floats.
Okay,
so, and actually one thing that's interesting is as you add more and more positive charges in the middle there, and as you move up the periodic table, these guys actually shrink in, but there's more of them. So you end up with like something with way more massive than hydrogen is about the same size as hydrogen in volume. I should say same volume as hydrogen. And then you end up with, I think, even though uranium is 238 times more massive because it's got a lot of neutrons. It has the 92 protons, but it's got like 160 something. It's got about uranium 238. So you can do the math. Subtract out 92 protons, you find out how many neutrons. It's something like 3 times the size of hydrogen, even though it's 238 times as much mass. 238 because it's got all those neutrons and protons. A lot more massive, and yet in volume it's only 3 times the volume of hydrogen, because they're pulling in, all those shells he's pulling them in tighter and tighter than, say, the hydrogen guy is because of all that charge. Okay, we covered that. We covered why we fill balloons with helium and not hydrogen. Okay, now you might say, wait. You're just telling me that you can shrink the shell when before you told me that it was set by the de Broglie wavelength of the electron. So why can we shrink it now when before you said it has to be quantized? Remember, it's still quantized. Even when we shrink these shells, they can't just go in the middle when they want. What's different? Well, remember, the de Broglie wavelength depended on the momentum of the electron. And as you're shrinking those shells, the momentum, those electrons actually are changing their momentum a bit, because they are having the same way that when you're closer and closer to a super heavy object, to be in satellite motion, you'd be going faster and faster. It is actually changing the speed of those electrons, which do change. It's still quantized. You're still only able to follow, certain levels here, but it does shrink. The de Broglie wavelength is slightly different here. Okay, now let's get back to the really weird thing I promised to tell you about the double slit experiment. Okay, Stevie, can you move that?
Down here.
Okay, good job, Drawing. It's just drawing a solar system here. Okay, so the really weird thing was they said, okay, can we measure, if light really is a particle that's acting like a wave here, can we measure when we shine a photon, which photon it went through? Did it go through which slit did it go through? Did it go through slit A or slit B? So they put these little detectors here to find out which hole is it going through? And when they put the detectors there, this is what happened. Light acted like a particle. They got a little bunch of white here and a little bit here.
What?
Light goes through. Then knowing which slot the photon went through made light act like a particle.
How did they measure it?
That is a very good question. And that has to do with, there's all these debates about this, that, and the other, and they've tried various thought experiments. Oh, thought experiment is a thought experiment. They've tried various experiments, and there's a really famous one that involves this thought experiment involving a dead cat. Can the cat be dead and alive at the same time? And quantum mechanics gets wild. I mean, it gets
Wait, but they
wild.
could see the pattern and know that it was.
But one of the things in quantum mechanics that just blows everyone's mind is that knowing something, knowledge, finding something out, collapses, what we call collapses the wave
But
function.
wait, how do they know that it was waves like that then?
Because of the interference pattern. That's how they know it was waves. But knowing when they put a detector, it collapsed it down. So there's people run with quantum mechanics.
But what did the
They try to come up with
detector
various
do?
theories. They come up with interesting,
Also with the
and
cat.
dubious medicines based on quantum mechanics. They do all sorts of interesting things with it. But quantum mechanics
Wait,
is
so if
one
you
of
put
those.
the cat in a
well,
glass box, you could see if the cat was dead or alive?
if you can see it, then you're measuring it, and that's different.
But then wouldn't the cat know
Okay,
if it was dead
we're
or
not
alive?
discussing the
The
cat.
cat
today.
would know if it was dead!
We will not
Or
discuss the
alive.
cat fully today. But what we will say is that what quantum mechanics shows us is that knowledge collapses the wave function. That knowing something changes it. And it's like, it's weird, it gets weirder and weirder. And it strains our minds. It shows us the limits of our understanding of reality. Even when we're just talking about things like particles and waves. Okay, can you stop the video?
Okay.